Hello, and welcome to the Introductory General Chemistry Lab. I'm Kevin Kolack. I'm one of the authors of the lab manual, and I'll be performing all of the experiments with you so that you can see how they're done. If this is a remote class, you can hopefully almost experience it as if you were there. The chemistry lab is a very important part of the lecture class in that it supports the material that you would learn in the lecture and gives you some hands-on practice. Now, I know that the vast majority of you are not going to be chemists. I've taken a poll in my class every semester that I've taught for the last 30 years, and only one person has ever said that they intended to be a chemist. And had my professor asked me that question when I was taking general chemistry, I would not have raised my hand either, and here we are. The important thing is to realize that you have to take this class, or you are taking this class, for some very valuable reasons. You're going to be reading some very detailed instructions using techniques that you may not have done before, and get some really successful results. Or maybe some not so successful results, and have to explain why you got the result that you got. So chemistry lab, whether you intend to be a chemist or not, and most of you I'm sure are not, is a ridiculously valuable experience, and that's why it's required to go to medical school, to become a pharmacist, to become a PA, and certainly, of course, to become a chemical technician. So let's jump right in with experiment 1, physical properties of matter, density. Now, you can do parts 1, 2, and 3 in any order, the density of a unknown solid, unknown liquid, and confirming the density of air. You can do those in any order, but we will go in the order that they are written in the lab manual. I will pause at certain points because some of these lessons will be converted to something called play-posit lessons, where when you're watching the video will stop on its own and ask you a question. Alternatively, your instructor, if they're showing you this video, may stop at certain points and discuss or ask questions. And of course, the final possibility is that you're just watching this video on your own, and maybe you should stop it when I suggest that you stop the video and see if you can answer the question. And then, of course, once the video starts up again, or when you start the video up again, I will answer the questions. So here we go with density of an unknown solid. Of course, I'm starting the lab wearing my goggles, wearing my lab coat, and wearing my gloves, even though nothing that we are using in this lab is toxic or hazardous. Why am I still wearing my goggles, my lab coat, and my gloves? Because establishing good habits is an important part of this lab, and an important part of an eventual job for you. If you become a garbage man, and you'll make a whole lot more money than me if you do become a garbage man, garbage person, garbage disposer, there are safety procedures involved so that you don't injure yourself. And there are procedures and standard operating procedures that you have to learn. So this is applicable. I promise you, it is applicable to whatever job you eventually end up doing. And those are my goals for you coming out of this class. I tell my students this every semester. I would like for you to get out of this class with the grade that you would like, to graduate, to get a good job, to not get fired, and to not kill anybody. Those are my 5 goals for you. Let's do first lab. So I have a balance here that I will use after I do step 1, which is obtain a metal bar, record its color on the data sheet in pen, not in pencil. So why might you want to record your data in pen and not pencil? Well, this is very important in a variety of fields, because if you are an airline pilot or a police officer and you record your data in pencil, you got a high probability of being fined, if not fired, by a supervisor, because pen is permanent and pencil can be erased and changed. If you work in a hospital and they haven't switched over to electronic record keeping, which would be shocking, but it's possible, I suppose, and you record in pencil, you're going to get fired because you're going to expose the hospital to enormous liability. So you will record your data in pen. You may have a metal bar that looks this, sort of brownish yellowish. You may have a metal bar that looks like this, sort of shiny and silvery. You may have one that's like this, sort of dull and silvery. Now, your instructor has access to 10 different sets of data. So they'll give you sample data. So reading the number off of this balance isn't particularly important, but I'll just choose the yellowy one at random. So I would record on my data sheet, this is not particularly shiny, it's sort of dull, and yellow, gold maybe, whatever you'd like to call this. All right? And then I'm going to weigh the metal bar and record its exact mass on the data sheet. So my balance says 0. Now notice please that I'm calling this a balance and not a scale. A scale is what you have in your bathroom to measure your weight. This is a balance. It is a precision mass measuring device. It would give you the same numbers on the screen on the moon as it does here. If you took your bathroom scale to the moon, it would give you about 1/10 of the value that it gives you on Earth, because weight is a measure of a force due to gravity. Mass is constant throughout the universe for a particular object. So if my numbers weren't reading 0 here, which they pretty much are, it's a little bit windy in here with the fans on today, I would hit the 0 button, which is sometimes on certain balances called a tare button. Not T-E-A-R, but T-A-R-E. It sets the balance to 0. Even if there was something on it, I'll choose a different bar. Right? There was something on this. Let's say I had a flask or something. I could tare it, and so then the balance would read 0, whether you can read this number or not. And then if I took it off, of course, now it's reading a negative value. Let's see if I can. You should never move a balance, but I'll move it closer where the numbers are a little bit visible to you folks. Okay? So I'm going to weigh my metal bar after I 0 the balance. I'm going to weigh my metal bar. And when I say weigh, I mean obtain the mass. It's just awkward to say obtain the mass every time. So I mean obtain the mass, but I'm going to say weigh. Weigh the metal bar and record its exact mass on the data sheet on line 1B. So I would write down 53.40, 53.39. Some people, when I look at their data sheets, I don't know why, leave off a number or round it to 53.40 or 53.4. That is not okay. The lab is about precision and accuracy. And precision applies to, from chapter 1 of the book, how many decimal places you have. How well do you know that number? Now this balance is guessing that last digit. It says right on here, maximum of 300 grams with a deviation of plus or minus 0.01. So this might be 38, it might be 40. The balance is guessing for us because it's digital. Were it an analog instrument like a ruler, you would be guessing the last number. You always have to guess one more digit than is available. This balance is doing it for us. So I would go to my data sheet and I would write down on line 1B, because 1A was the appearance of the stuff, I would write down the 53.39. Okay? Now, on to step 3. I have a 100 milliliter graduated cylinder, which is a precision measuring device for liquids. It says on it that it will to contain, TC, to contain at 20 degrees Celsius. Now it is much warmer than 20 degrees Celsius in here, so we might have some expansion of a liquid, which often happens. As you increase the temperature, the liquid tends to expand, but we're going to disregard that. Okay? I'm using a 100 milliliter graduated cylinder because if I tried to use a 10 milliliter graduated cylinder, like I'll use in the next one, it just doesn't fit. Okay? So it says to put about 50 milliliters of water into a 100 milliliter graduated cylinder. About 50 milliliters. The lab manual uses its language very carefully because I've written a few editions of it at this point, and I choose my words for a reason. About 50 milliliters means exactly that. About. Not exactly anything. About. So I'm just going to put some water in here. Take your time to be exact when you need to be exact, and take your time not to be exact when you don't need to be exact. Did it say any sort of special deionized water? No. Just water. Did it say exactly 50 milliliters? No. It said about 50 milliliters. So I need to measure the exact volume. So if you look here at the meniscus, you can see that it is between, I'm going to look at this here, it's a little bit above 60, okay? Now if we looked really carefully, and it's going to be hard for you to do this because I can't get this exactly at eye level, at camera level. If you look really, really, really carefully, and I'm going to get my eye level down to it so I can see, it is between the 62 and the 63 milliliter line. Really, really, really close to the 63 milliliter line, but between 62 and 63. I cannot just write down on my data sheet 60, 61, 62, 63. It's close to the 63 line. I'll call it 63. That's blowing our precision. All right, this is marked in 1 milliliter increments. So I know that it's between 62 and 63, but really, really, really close to 63. And so that's what I have to write down. Well, what am I going to write on my data sheet? Really, really, really close to 63? No. I am going to estimate that last digit. I'm going to write down 62.9 milliliters. Now, you don't have to write this number down because you'll be supplied some sample data, but 62.9 milliliters is my volume without the bar. Now, step 4. Hold the graduated cylinder at a 45-degree angle and slide that bar whose mass we made to the bottom. Okay? Now at this point I say stop. What's going to happen if I just drop that sucker in there? Well, if I take this out of the stand, you can see that the bottom of this graduated cylinder is glass. So I leave it to you to figure out what would happen if I just drop this puppy in there. All right. Now, step 5 says record the new volume of water in the graduated cylinder. And so again, I look at the bottom of the meniscus. Again, this is a little bit of an angle, so I can't really show it to you at camera level. But I'll get down there at eye level so that the meniscus is nice and flat for me. Well, curved, right? You'll learn this in a much, much, much later chapter. Water adheres to the glass with stronger forces than it coheres to itself, and so that's why you have a U-shaped meniscus, it's called, at the top of the water. If this were mercury, it would be toxic, and we wouldn't do that. It would be an inverted meniscus because mercury coheres, cohesive forces are stronger than its adhesive forces to glass. So I need to get my new volume here. And again, it is 65, 66, 67, 68, 69. It's between 68 and 69, but really, really close to the 69 line. And so on my data sheet, I record 68.9. Okay? 68.9. And then step 6 is calculate the volume of water, where we started, subtracted from where we ended up. And that will give us the volume of space that our metal bar is taking up in our liquid. It has submerged in the liquid, displaced the liquid in an equivalent amount to its volume. And so we know the volume of the bar. This is a great way of figuring out the volume of an irregular solid, is you submerge it in a liquid. Now if it floated, it'd be more of a challenge. There's ways of getting around it. You put a screen over it and push it down, but this works great for us. So we have the volume of our bar by measuring the difference. So since this is just water, I'm going to pour it into the sink. And I have my bar to put back after I dry it off where I got it from. Then we can calculate the density of the bar because we have its mass and we have its volume. Think of the definition of density. Mass per unit volume. Mass divided by volume. Mass over volume. There's a lot of different ways to say it, but a lot of times in chemistry, the unit will tell you how to do the problem. You should really, really, really focus on the units. If I know the mass of something, and I know the volume of that same thing, I can calculate its density. Conversely, I could flip that around. If I knew its density by looking it up, and I had its volume, I could calculate its mass. Or if I knew its density and I had its mass, I could calculate its volume. Well, why would I want to do that? Well, let's say I have to ship a bunch of it, and I want to know if it'll fit in a box. Or if I'm a truck driver, and a lot of my friends are truck drivers, because I was a firefighter for 10 years, and a lot of those guys were truck drivers on their days off. And if you drive an overweight truck, you will get fined, and it's on your license. It's not on the person who filled up your truck. And so you might need to calculate the mass of your truck contents before you head on down the road. And so these calculations are useful in a variety of different fields. So from the density of this bar that you will have calculated either from the sample data that your instructor gives you or made up data that your instructor gives you, or I suppose you could have written these numbers down that I called out in here, then you could flip back to table 1 where there are a variety of gas, liquids, and solids listed with their density. You can only look at the solids for this one because obviously it's a solid, and you can figure out its identity likely. I don't say that you can absolutely figure out its density because it's one data point. Maybe you can confirm its density. Oh, I think that this is X metal because of the way that it looks. All right, well, this is probably not silver, right? Because it's not silver. It's also probably not gold because tuition here isn't high enough to buy a gold bar, okay? So it's probably not gold. And then if I look on the density of the various solids for one that looks this color, maybe I can figure out what it is. And if I had something like this is probably not, it doesn't look like a trumpet, so it's not brass or saxophone, right? This one wouldn't be brass because it's not the right color. Even if it had a density that was close, it would be the wrong color. So we have 2 data points for confirming or at least guessing what the identity of our solid is. So there we go. That was part 1, identifying an unknown solid based on its density. Let's move on to part 2, determining the density of an unknown liquid. And that's exactly what I have here, unknown liquid, right? It's liquid number 1 if you're keeping score at home, and you do need to keep score because the unknown number is line 2A. Obtain an unknown liquid, record its number on the data sheet. Again, there's a data file that your instructor has access to that has a variety of different unknowns listed, but if you want to use unknown number 1, if your instructor is having you just write down the data that we're recording here, we have unknown number 1. So, it says, step 2, weigh an empty 10 milliliter graduated cylinder. Now, interestingly, this 10 milliliter graduated cylinder says on it, it'll focus, come on, focus for me. I don't know if it will. Let's see if I can put my finger on it. That might help. This one says TD at 20 degrees. Most graduated cylinders, like the last one we saw in part 1, are TC. They contain a certain volume. And this graduated cylinder is marked TD for to deliver, meaning if I fill it to the exact 10.00 line, and more on that in a moment, then I can pour out exactly 10.00 milliliters. Now, why am I saying 00 on this one? Well, if you look really closely, this graduated cylinder is marked in tenths. Actually, it's marked in 2/10, which is a little bit annoying, but it's marked in tenths. The 100 milliliter graduated cylinder was marked in ones, and so we guessed, is it between 61 and 62? We guessed by how much. This one, we can see that it's going to be between the, let's say, 9.8 and 10.0 line. And so we have to guess the hundredths place. But step 2 says weigh the graduated cylinder empty. My balance is already on 0 tared, and so I have my graduated cylinder's mass at 28.72 grams, not touching the table. If you touch the table, sometimes the mass changes. Let's see if I can get it to do it. There we go, just a little bit. I guess I'm not that fat today. All right, you don't want to touch the table when you're weighing things. It's a bad idea. So 28.72 is the mass of our graduated cylinder empty. Now notice I'm not rubbing my fingers all over this. I have gloves on. So I'm not getting fingerprints and greasy fingers and whatever fried chicken you had for lunch. I'm not getting that all over the graduated cylinder. It's staying nice and clean, and there's nothing in it. You know, if I had washed it ahead of time, it might have droplets of liquid in it, and I would need to dry those out really, really, really well. But I didn't wash it ahead of time because I can see that there's nothing in it, and it doesn't matter if my unknown gets contaminated, because I just need the mass of it as it is now, and then after I put some liquid in it. So it says use a funnel to carefully place approximately 10 milliliters of the unknown into the graduated cylinder and weigh it with the liquid. Between 8 milliliters and 10 milliliters is fine, but I definitely can't go over 10, because if I go past the 10 line, there's no more lines, and you can't get a reading because there's literally no more lines. So somewhere between 8 and 10 milliliters, so that I have enough in there to get a significant mass. So I'm going to put my cap down, cap up. All right, if you put it like this, then you can get stuff contaminating the lip, and when you put it back on the jar, maybe it goes in the jar or just contaminates the bottle. So I always put my cap up. Again, I get down around eye level, and I pour somewhere between 8 and 10 milliliters in there. And there we go, between 8 and 10. Put my cap back on so it doesn't evaporate or anything fall into it. So again, I got a little bit over 8, less than 9, and I need to get the exact reading. So if I get down there to eye level, sometimes it helps to put your hand behind it or a piece of paper with a line on it to get an exact reading, but I've kind of gotten some practice at this over the years. So this is between the 8.4 and the 8.6 line, but it's really close to the 8.4. So I'm going to call this 8.46. If it was exactly halfway between the 8.4 and the 8.6 line, then it would be 8.50. But it's not. It's a little bit underneath halfway between 8.4 and 8.6. So I'm going to call this 8.46 milliliters. Okay? And so I would fill that in line 2E. Okay? Then the next step says record the exact mass. My balance is tiered. It's starting at 0. Okay? Again, should this be more or should this be less than it was empty? Pretty easy question for you. 35.43 grams. 35.43 grams is the mass of my graduated cylinder with the liquid in it. So this is good. I have the mass of the graduated cylinder empty, and I can take that away from the mass of the graduated cylinder with the liquid in it. I have the volume of the liquid in it. So once again, I have a number of grams. I have a number of milliliters. Grams per milliliter is the units of density. And so if I just divide grams by milliliters, I will again have a density, and I can flip back to table 1.1 and look at the liquids this time and determine what this liquid is. Now, smelling, tasting things in the lab, putting them on your skin to see if they burn or feel funny, generally a bad idea. But we can carefully smell this and see if it's something that we might recognize. So I'm going to carefully wave this to my face, just to get an idea. Have I smelled this before? Now this isn't on your data sheet anywhere, but just gonna have a second data point for us to know. And to me, this doesn't smell like nail polish remover. It kind of smells like vodka. So maybe this is some kind of alcohol. It might be drinking alcohol, it might be rubbing alcohol, it might be wood alcohol. So you would never take a snort of this and see what it is, because 10 milliliters, if this is wood alcohol, will permanently blind you. It's not a whole lot, it's a shot. 10 milliliters of wood alcohol will blind you, and this is why people in other countries that don't have access to alcohol and don't have access to a good life sometimes kill themselves or go blind drinking like floor cleaners and stuff, because they look at the side in the ingredients list and it has alcohol on it, and they think, oh, drinking alcohol, and they are sadly mistaken. I only drank a little of it. Yeah, 10 milliliters of wood alcohol, methyl alcohol, will permanently blind you. That's it for the density of an unknown liquid. You calculate the density of the liquid, record it on line 2F, and look at table 1.1, and see what you think it is, and put that identity on line 2G. Lab 1, density. Section 3, the density of air. Confirming the density of air, because we know what the density of air is, okay? You can look on table 1.1. The density of air is 1.185 grams per liter. Now, you could look it up. It's not on here, I don't think. No, it's not on here. But you could look up somewhere, Google it maybe, the density of nitrogen, and see what the density of nitrogen is. The air that you're breathing, and the air in this room is currently extremely hot, but anyway, is mostly nitrogen, about 78% nitrogen, 21% oxygen, and 1% other stuff. That 1% is mostly carbon dioxide, but there's water vapor and argon and other things in there too. So we're confirming the density of air. If we had an unknown gas, say trapped in a balloon or something, we could use the same procedure to figure out its density. Just weigh the balloon with the gas in it, and then weigh the balloon with the gas not in it. As long as we had the volume of the balloon, which we'd have to figure out some way, we could again get a mass and a volume and know by calculation the density of the unknown gas. But we're just going to do air. So to do that, I got this densitometer here. This densitometer holds 500 milliliters. That L should be a capital L, but it's not. Milliliters, capital L is for liters, and M is for milli. So 500 one-thousandths of a liter. So this is 500 out of 1,000, half of a liter. 0.500 liters. Okay? Exactly 0.500 liters. Right? Technically, the number 500 only has one significant digit, if you've gone over that in class. We're going to say that this is exactly. So we could even go more zeros if we wanted, 0.5000000, whatever. But the three significant digits that we're going to call this is enough. 0.500, that number has three significant digits. So 0.500 liters is three significant digits for our calculations. We're going to say that this is exact. We're not going to limit our numbers by that. By saying it's one digit, that would be bad. All right, so again, not touching the table. The valve is open, right? Valves, whichever way the handle is placing is where the hole is. So the hole is now out through this nipple into the room and into the densitometer. So it's open. So what's filling this densitometer now is it's full of air. I'm going to weigh it full of air because that's what it says in step 2. Open the valve on the densitometer. Oh wait, no, it says do it first. Read your instructions. Open the valve and hook it up to our vacuum pump, and we will get all of the air out of our densitometer. 500 milliliters, 0.500 liters. So the valve is open so that we can suck the air out. Put on the hose. It's going to be a little bit noisy. Hopefully the noise control will catch it. Notice I'm hanging onto the densitometer so it doesn't flip over. There we go. So as the air gets sucked out of this thing, you'll see this little needle going down, down, down for the amount of pressure in the can. Not really going down much at all, which is not particularly good. Let's see. twist the knob if that does anything for us. Nope. Let's take this off and see if it's sucking at all. Maybe just our gauge is no good. Yeah, definitely sucking. Yeah, so our gauge appears to be broken. So we're just going to put it back on here and just give it a good minute of pumping down, as they say. Sometimes some smoke comes out of here. It's just hydraulic oil from the pump escaping. The filter is on there to try and prevent that, but you just wouldn't want to inhale it. But otherwise, a relatively safe procedure. This thing has got some nice thick walls to it, so it can't collapse. You might see that the bottom is curved a little bit so that it doesn't implode. Alright, so we're doing step 2, opening the valve, attaching the hose from the vacuum pump, and we're evacuating it for a couple of minutes. Step 3, when the pressure gauge has stopped moving, even if it's broken and not reading total vacuum, we will close the valve. Right, handle is sideways, so that means the hole is perpendicular to the hose, and no air can go back into the densitometer. We will turn off the densitometer, and we will remove our hose. There should be a little, just refilling the air into the hose. Let's see if we can hear it. No. All right. And then, step 4, weigh the evacuated densitometer. Our balance was taired, not touching the table. 175.98. 175.98. Okay? We might need to use a better balance than this one, but we'll try it out. Step 5, open the valve. Let's listen. The air has now refilled, and we'll weigh it. It was 175.98. $176.56. Will that number be greater or less than the number that we recorded? It was 175.98. It's 176.56. Is that what we would expect? I certainly hope so. And if we could subtract the mass of the densitometer with air from the mass of the densitometer without air, then we have the amount of air in grams that fills the densitometer. And we can calculate the density since we know the volume and we just obtained the mass. And then we can compare our calculated value to the 1.185 from table 1.1. And this is a great step 3 here, or part 3, for figuring out why do we have a mass that is greater than or less than, a density that is greater than or less than the expected value. There are reasons that you can think of. The volume is the volume, okay? That can't be the problem in this lab. It has to be the mass. So what could make the mass be too high or too low, and what effect would that have on our calculated density, which is mass divided by volume? If the mass was too big, bigger than it should be, of air, then since mass is on top in the equation, the density would be bigger than 1.185. If the mass of air is too small, then the mass, again being on top, the density is going to be too small, less than 1.185. Well, what could make that mass be too big or too small? In every single lab that we do this semester, that's the kind of thinking that you have to undertake. What could go wrong in this lab? Well, we're finding a mass and we're finding a volume. Well, volume is volume, at least in part 3 here. It can't be wrong. I mean, I guess if this densitometer was seriously dented somehow, that might mess things up. And then the volume could be wrong. But it's not. It's not dented. The volume is the volume. So then the mass is the only thing that could be off or wrong. Well, what could make that mass be off? or wrong? Got to think about those things for your discussion of your lab report. That's the end of the first lab. You've made it. Congratulations. Make sure that you have a good discussion with your instructor over all of the techniques that you've learned in this lab, all of the jargon that you've learned in this lab. That's another reason chemistry class is required. When you start a new job, there's going to be jargon, there's going to be acronyms. You have to learn new words. You do that all semester. You learn new words, and that's a valuable, valuable skill. See you on the next lab.